started. Okay, so what we can do is we can look at law of refraction, and basically I'm going to draw just a few objects. We have a prism, right? Like that. Triangular prism, rectangular prism, and then we have another triangular prism here. Okay, so not perfect, but again, we're trying to see how the light would travel through these prisms. So light going through the middle part will basically not refract at all. It doesn't mean it's not going to slow down going through the medium, but it will go right through. Since the angle of incidence is equal to 0, the angle of refraction will also be equal to 0, according to Snell's law. Let's move here. Now, excuse me, the light going to through this prism here, also, let's say we're shooting the light so that all the rays are parallel, right? So it's going to hit somewhere here. Just move a little bit this way. And if you drew the normal, let me see if you can do that. Normal. Maybe we can make it a little thinner, like that. And if we follow Snell's law, then we should see that the light would bend somewhat like this. Okay, somewhat like this. Now, over here, the light will be exiting the prism. So we're going to draw another normal. Again, a thinner line. So somewhat like this. And the exit angle here has to be greater than the angle inside the prism. So we should expect that the light will come out like this. So it'll bend even more like that. Okay. Now if we follow the same procedure here, basically we'll find the light comes in like that, right? And then see, make it straight. Then it goes through the lens, through the prism, like that, right? And then it's gonna bend more. Let's go through the focal point. So I mentioned the focal point. You can arrange this so that a particular beam, particular rays will meet here at the point. But the truth is that if you try to shoot the rays from all positions here, they are not likely to meet at the same point. Actually, you can figure out that there will be a certain region here where light would concentrate. Now, instead of this, we'd have a much smoother curvature. Then probably have much smoother transition for the rays. So here we have the rays traveling this way. Okay, like that. And they're concentrated here. So if you had a lens, so I'm going to try to draw that. So it'll be a lens, which will be thicker in the middle and thinner on the edges. So this will be called convex lens. Convex lens. Actually, like more like formal name will be convex lens. And basically, its middle part is thicker than the edges. Okay, and you can imagine that these are parts of the curvature of the circle. So if we were to draw a circle, so it's like this, right? So that's the part of the sphere, right? The surface of the lens would be part of the sphere, and the other side will also be part of the sphere. Ideally, they should be of the same curvature for a simple lens. Obviously, the ones that is drawn here is not the same curvature on both sides. Okay, So this will be called convex lens, simple convex lens, and we're going to work with really thin lenses. And for our diagram purposes, we'll not draw the lens each time, which instead we're going to draw like the line like that, and we're going to draw two arrows pointing outward, which means that the edges are thinner, the middle is thicker, but we will work with so-called thin lens. So this will be a thin convex lens. The reason we need to deal with thin lenses is that we want to avoid certain problems, and those problems will be mentioned later. Okay, now if we were to arrange prisms in a different way, so let's say we're going to have the middle prism will be the same rectangular piece, and on top and the bottom we're going to attach truncated or trapezoidal prisms, right? Something like that and something like that. So this models different behavior. So if you follow the light, then you will see the light coming through this, obviously will go right through. The light coming through this one will bend towards the base of the trapezoid, the bottom base, I mean the larger base. So that light will end up actually being diverted like that, and the light coming from here will also be diverted somewhat like that. Okay, so what's happening here is the light is being diverted away from the central line, like so. So the central line, or the axis, we can call the axis, right? It's called the principal axis. And in case of this kind of lens, the light is being diverted or diverging from the center. So if I were to draw this lens, it would look somewhat like this. Again, ideally they should be like spherical surfaces. So we're talking about basically spherical lenses. They're not ideal, but they work. They're easier to manufacture. This is a really ugly lens. Okay, so let's see if we can have steady hand. No. One more attempt. Somewhat like this. Okay, so this is thicker on the edges and thinner in the middle, and it will be called concave lens. Concave, from the word cave, concave, or in this like more formal way, we can say called concave lens. If the two curvatures are different, then you have to say concave lens, and then each face or each side will have a different radius of the curvature lens. If you want to label it on a diagram, then you draw, again, straight line. And this time the arrows will be pointing inward, meaning that we're indicating the edges are thicker than the middle part. And it's a thin, it's going to be a thin concave lens. So again, we'll talk about the problems with the thicker lenses later. There are certain problems that people try to avoid using all kinds of techniques. So this lens is can also be called converging lens. Converging lens. Why? Because it's going to converge the light coming from the source. Like the source will be on the left side, the light converges to the focal point, and then thus this one will be called diverging lens. Diverging lens. That's how we spell it, right? Diverging lines. Okay, any questions about this? So this is the model. This is how it looked like in reality, like cross-section of the lens, convex and concave. And this is how we're going to draw them in the diagrams, ray diagrams, because we want to make sure that the lenses are really thin and don't suffer from certain problems that we'll talk about later. Okay, so then let's move forward. Next one. So I'm going to draw this now as a principal axis, right? We're going to put the lens here, and we're going to draw one diagram. So let's see if we can do that. So this part will be called ray diagrams. So I'm going to put it somewhere here. Hold on, let me move the whole thing down. Ray diagrams. Ray diagrams. Okay. So first of all, we have to identify focal points. And let's say the focal point will be somewhere here, and then equally distant here. Okay, so somewhat, maybe a little closer, I don't know. Yeah. Ideally, you want to draw it on the graph paper. So this will be focal point because we have two curvatures, right? Each curvature creates its focal point. And if we move double the focal point, we will get the center of each curvature. So we can write down that the radius of the curvature of the surface of the lens is equal to twice the focal distance. I'll use lowercase f. Sometimes people use capital F. So don't confuse it with frequency. So this distance over here will be radius. So if we were to draw the circle, this would be the center of the circle, and we'll just draw the circle like that, right? And this will be half of that distance. We're going to label this as F1 and F2, since we have two surfaces, and this is a transparent medium. So this is double F2. Oh my God. I'm going to have to cut this from video. And this is 2F1. We're going to make an assumption that F1 is equal to F2. So relatively simple lens, okay? What's going on here? All right, so thank you. Let's try to draw a ray diagram. Let's just jump into it. So we're going to draw an object. So our object will be basically a candle. I'm going to put the candle here. The reason we use the rectangular objects, or sometimes we're going to use objects that look like a triangle or like an arrow right there. So it will look like an arrow. Oh, go away. Go away, go away. So it will look like an arrow like this, right? So the reason we use this kind of a simple object is that historically people used candles for the objects, but also as a source of light. So you would not have other sources of light to be confused with. So you have one object which represented both the object and the source of light. Okay, so that's the reason you could use any kind of object here. The more complicated it is, the more difficult it is to trace the rays and then to figure out the image. So we're going to use a rather simple object, geometrically simple object. So the way to do this is you draw the P ray or parallel ray, and all the parallel rays, in ideal case, should converge to the focal point. So So this one will have to go this way. Now you have to understand this is an approximate diagram here right now. Hopefully it will work out. But if it doesn't, then you understand why. The next ray will be the F ray. Let me actually label this thing. This is going to be P ray. P ray. P stands for parallel to the principal axis. Okay, so next one will be F ray, which means it's going to go through the focal point. And by symmetry, the F ray will become parallel as it passes through the this thing. So I already know it's not going to work out because something is off. Okay. Now that should be enough to find the image. No, I'm going to cheat a little bit because I want the diagram to look better. So let's see if I can move this point here. So I'm going to cheat a little bit. And I'm going to put it here. Okay. Ideally, when I do it on the board using a ruler, it works out perfectly, almost always perfectly, because you have to use a ruler, proper tools. So we're done. Basically, we can say that the image has formed right here. So I'm going to just draw an arrow here. Oops. Color. So many things. So this will be the image. Like that. Let me just draw the object here as well. Okay. So ideally, it will get this. And there's a formula to calculate this thing, and we can actually write down this formula. It's called thin lens formula, or thin lens equation. Thin lens equation. So let's see. It's going to look like this. 1 over F, 1 over the focal distance, equals to 1 over DO, blue, plus 1 over DI. So F is the focal distance. That's the distance measured from the center of the lens towards the focal point. Direction is important, by the way. So for the convex lens, it's a positive number. DO stands for distance to the object. And DI stands for the distance to the image. So here we can indicate that. So distance to the object will be this distance over here. DO. Again, if we were to do like proper vectors, then we have to actually remove this thing. And DO is measured this way. Thus the DI will be measured this way. So that's a positive direction for the DI. Okay, and then we also have like a vertical direction. So this will be positive, and this will be negative over here. Negative. So our object is upright, right side up, right? But the image is upside down, so it will be in the negatives, right? Now we also have a magnification formula. Magnification. So magnification looks like this. M equals to minus sign DI over DO. So it's basically how many times the image is larger than the object. Okay, minus sign here is also important. Okay, so let's try to figure out this for the double focal distance, right? So we have 1 over f equals DO is equal to 1 over 2f. So we're looking for the DI. So from here, you should get the DI must be equal to 2f. Are there any questions about how we got 2f for the DI? So I suppose there are no questions about how we got DI. It's about addition of fractions. Okay, so 1 over f equals 1 over 2f because this is given. And let's say we're looking for the DI. Okay, can you solve this equation for DI?
Like 1f equals 1 over 2f?
1 over f minus 1 over 2f will be equal to 1 over DI, right? So if you can solve this for like you will get, yeah.
Oh, I see.
Okay, okay. Okay, so this leads us to this. So basically, first thing you can, first conclusion you can draw that the image will be at the same distance as the object when DO is equal to double the focal distance. The second conclusion you can draw is that magnification is going to be negative. So 2f here and also 2f here give us -1. So the image will be the same size, and the minus sign tells us it's upside down. So we can describe the image as same size, same distance, just 2f. This is specific for this situation, okay? It's not always the same thing. Same distance, same size, and it's upside down. Upside down. People use another word, inverted. Inverted. And it's also real. Real. How do we know this image is real? Is that because you know that because it's formed by real light. So real light is converging here. So you can actually project it onto the wall and then you will see it on the wall. Or you can create like smoke conditions where the image will be kind of hovering in the middle of the air. So it'll be just hovering and then the image will kind of be visible when tiny smoke particles are reflecting that light. Okay, without anything to be reflected off, you won't be able to see it there. The eye is actually, the eye, where's the eye? The eye is actually here. So if you were looking through the lens at this object, then you would see that the image would be somewhere here. So it'll be upside down. It will look like the object is closer to you, right? Because physically the image is right here. Okay. Any questions about this? No questions. Okay. So let me see if I can show you something. Let's see if we can, hold on a second, stop recording.